Okay, there we go. Let's go.
Okay, well, hi everyone. I'm Sarah Chieng, and today I'm going to be presenting the weight streaming paper by Cerebras. So I dropped the paper in the chat, but the paper is called Training Giant Neural Networks Using Weight Streaming on Cerebras Wafer-Scale Clusters. And so this paper is a paper introduced by Cerebras about weight streaming. And
Do we lose her?
She seems to have just paused. Yeah. Oh my God. That's a really awesome, awkward time to pause. Let me just see. I'll text her. It's funny because she's upstairs. Hey, you paused. Oh my God, what an awkward time to come down.
Let's do some of her background. Cerebras, chip company. They have big chip. Oh,
is
back.
it working now?
Okay, you're back. You're back. You're back.
Yep.
Okay, I'm so
Big
sorry
fat
about
chips.
Not potato chip, GPU chip.
Wafer chips in this size.
Anyways, sorry, I don't know where it froze. If I freeze again, let me know. Hopefully it doesn't happen again. I switch Wi-Fi networks. But basically this paper is called Training Giant Neural Networks Using Weight Streaming on Cerebras Wafer-Scale Clusters. And this paper covers weight streaming, which is a training technique, training execution flow by Cerebras that separates parameter storage from primary compute. And by doing so, you're able to efficiently and scale the training of large language models. And so usually you can imagine, your weights are stored directly on your compute units, but this paper talks about how you actually store externally and you stream those weights to your compute units during training to allow your cluster to scale very quickly and easily. And so this paper was published by Cerebras, and Cerebras is a AI processor company. And their biggest thing is that they're building the world's largest and fastest AI processor. So their chip is called the Wafer-Scale Engine 3. So the Wafer-Scale Engine 3 is the latest iteration of their chip, although this paper talks about the Wafer-Scale Engine 2, which is just, a previous iteration. So I'll talk a little bit about the differences as well. And so for a little bit of context on, what Cerebras is doing and what this hardware is doing, a few weeks ago, Cerebras, you can do inference and you can do training. And, as Swix mentioned in the chat, a few weeks ago, Cerebras came out that the Wafer-Scale Engine 3 can serve Llama 70B at 2,100 tokens per second, and serves Llama 405B at nearly 1,000 tokens per second. So this, to give you an understanding, like this is about 70 times faster than anything you can do with an NVIDIA GPU or like running inference on an NVIDIA GPU. And so they actually have a way to kind of experience this very easily. So now I'll screen share. Okay. Let's see. Let me screen share.
Eugene, what is typical inference for you guys?
It's gonna kick me out, so I'll be right back.
Okay. Oh boy.
So typical GPU inference typically is within the hundreds of tokens per second.
For 70B, right?
Yeah,
You always have to say which size you're talking
for
about.
which size, yes. For 70B scale, if you want to do tensor parallel, throw 4 H100s at it, then you can, or 8 H100, you could potentially start approaching 1,000, but that's like burning a lot of money into just one batch size.
Yeah, and you use all the speculative decoding and all that. Yeah.
Yep, it's as far as I know, no one is doing that other than in some specialized benchmarks because it's just too expensive to burn an entire H100 node just for one request.
Yeah. Sarah, I think you're back, but you're not speaking.
Can everyone see the screen?
Yeah, all right, you're back.
Okay, awesome. So, this is, a public facing chat that Cerebras has. It runs Llama 70B. And it's like a chat GPT. It runs Llama 70B and then it's powered by, the Cerebras hardware. So you can ask a question like, tell me about World War II in great detail. And 2,500 tokens per second. So it's, generates all of that in the blink of an eye. So, that's just a little demo, and I'll put the link to this in the chat as well if anyone wants to like play around with it.
I got you.
Okay, thank you. Okay, and then yeah, so that is Cerebras hardware. So anyways, going back to the paper though, so the paper is talking about how you combine each of these different, so the Cerebras' main hardware is the Wafer-Scale Engine 3. And the Wafer-Scale Engine 3 sits inside the CSX, which is the entire system. And this paper, and that is one compute unit. And this paper talks about how do you combine multiple of these compute units to, work together and achieve that near linear scaling. And so before we jump into the paper, I thought it would be some useful context to talk a little bit about the Wafer-Scale engine that's like kind of the heart of this system, and really break down a little bit about the architectural design that is allowing Cerebras hardware to, serve inference so quickly, training so quickly, etc. So I have a couple of slides for this introduction portion. Let me know if people can't see, if it's not working how I think it's working, but hopefully everyone can see the slide right now. So this on the left is, a picture of the Cerebras hardware, the Wafer-Scale Engine 3. It is pretty large, as you can see. This is, the heart of, this paper, this heart of, what Cerebras is doing. It has about 4 trillion transistors, 900,000 cores, and 44 gigabytes of on-chip memory. And so for context and, as a side note, the paper does talk about the Wafer-Scale Engine 2, which is a previous iteration, has 850,000 cores, 40 gigabytes of on-chip memory, just, a little less powerful. And so, I'm sure everyone's wondering, everyone's much more familiar with the NVIDIA H100. And so now to kind of break down, to understand why Cerebras is able to perform at the speed it does, I want to compare it to the NVIDIA H100 and, one of the biggest bottlenecks and limitations that the NVIDIA H100 has. And so I'm going to focus a little bit on, the NVIDIA GPU. So in this picture, on the left, you have the Cerebras hardware. On the right, you have the NVIDIA H100. You can tell significantly less transistors, 80 billion versus 4 trillion. And, this size is pretty to scale as well in terms of, that is how small the H100 is compared to the Wafer-Scale Engine 3. And so to kind of, as I mentioned, understand, to understand the architectural decisions behind the Wafer-Scale Engine 3, I want to talk about the H100 and one of its biggest limitations. And so if you look at this picture of the H100, each of these, GPUs is made up of cores. And if you look at the red rectangle, that is one core. And these cores is what is actually making up, is what's actually doing all of the mathematical computations needed for, inference and training. And on the NVIDIA H100, there's about 17,000 cores on that H100. And so each of these cores, it needs access to things like the weights to actually do all of the computations. And on the H100, all of these weights is stored off chip. So there's a memory is located off chip, and this is what's storing the weights, during inference like KV cache, all those values. And so now you can imagine you have these 17,000 cores, and each of them are constantly needing to load and unload values from this memory, from this off-chip memory. And now you have this very, very significant memory channel bottleneck. So now in comparison to the Wafer-Scale Engine 3, so what Cerebras has done for the Wafer-Scale Engine 3 is that instead of storing all these weights and values weights and values off chip, Cerebras stores everything on chip in SRAM. So every single one of the cores on the Wafer-Scale Engine 3 has its own SRAM. So each core has direct access to each of the values that it needs to do its computations. And this design eliminates the need to repeatedly fetch weights from a central memory, which then significantly reduces the memory bandwidth requirements and power consumption of the Wafer-Scale Engine. And so that is one example of a very key architectural difference between, you know, what's out there like the NVIDIA H100 versus the Wafer-Scale Engine 3. That's really, you know, now that these weights and values are not having to travel as far, you're not having these memory bottleneck constraints, it's able to power things like inference much faster. So now that is kind of a little bit about the hardware. And so now kind of shifting gears and talking about this paper. So this is one system, and this paper is focusing on how do you combine multiple of these wafers sitting inside of the CSX system. How do you combine multiple of these units together to train very large models very fast and very efficiently and very easily? And so this system that Cerebras introduces actually has 3 different components. Sorry, to take a step back. So how I'm going to structure this part of actually going through the paper is I actually have some notes. I have a Notion doc of all the notes that I wrote up, and I'll present the notes next to the paper. But before we deep dive into the paper itself, I want to you know, give a really quick overview of what this system is looking for. What this system looks like. So the paper presents this weight streaming solution that has a couple of different components. The first is a CS3 CSX system. Those are the compute units. And instead of storing all the weights that the compute units need on the compute unit, it's storing it externally in an external memory service. In this case, it's called memory X. And during training, these weights are streamed from memory X to the compute unit, once during the forward pass, once during the backwards pass. And then the memory X is also what is computing the updated weights. And then this middle layer, this swarm X that you see, is basically that interconnect fabric that is connecting each of the compute units to the external memory service. So that's kind of a high level of what the different components in weight streaming are. And so now, okay, so this also, you know, better illustrates that a little bit. You have your memory service, all of your weights. These weights are streamed through the Swarm X, which is your interconnect fabric, to each of the different systems. And so now let's go through the paper. And so what I actually want to do, so here are some notes. It's a pretty long paper. It's around 35 pages of technical content. So to kind of make it easier, I've created these kind of like condensed notes that pretty similarly follows the paper section by section. But, you know, it's in notes form. It's a lot easier to digest. And then I also added a couple of, you know, like side notes, you know, like what are other people doing? What is the updated version of this since this paper was published a couple of years ago? And on that note, this paper was published a couple of years ago, I think in 2021, but the techniques in this paper are still very relevant. They're still used in production today, still very applicable. So what I want to do is actually, let me put it in the chat. Let me stop the share really quick. I'm going to put these notes in the chat. Thank you, Kyle. Yes. Let me know if this does not let you access it. Okay. So everyone, let me know if people are, okay, perfect. Thank you, Kyle, for confirming that you can access the notes. And so, yeah, so basically I'm gonna be sharing the notes. Sorry, let me reshare my screen. Okay, cool. So on the left, we have our paper, and on the right, we have these notes. We're gonna kind of be going through them together. And then obviously everyone has access to the paper and the notes as well. So you can look at it at your own pace as well. And one thing that I do want to say about these notes is that if you have any questions or comments or clarifications or things that you are like, this is unclear, or things that you think are missing, just please add a comment on the notes. And if there are ever any questions during this, the ones and like maybe I'm not able to answer it, like just leave it as a comment and I promise I will get to it and I will answer it in the notes and update the notes. But yeah, I mean, bear with me if there are things that I am not able to answer. But yeah, so now let's go through the paper. Okay, so it's just an abstract. And then, so yeah, so the first thing that this paper talks about is, just an overview of model training. I don't know the context of, or like the context of what people have, but we'll just go through it anyways. It's pretty straightforward. So this first section is just, how do you train a large neural network model? And what that involves is you have all of your training data, you process it in batches, and for every single batch, you do forward propagation, you compute the loss, backwards propagation, and you update the model weights. So for forward propagation, your model is, composed of different layers. Each of the layers, you do different computations. For each layer, you take the computation output and pass it to the next layer. And so in the first step, forward propagation, you're passing your training data through each model layer sequentially, and at each layer, computing the activations. And that's just the, the new computational output of, that layer. And then after you go through every single layer, you have the model's final prediction. And then you then compare your model's prediction to the actual value, the true label, from your training data, and use that to measure the prediction error. And now, once again, you go through your model layer by layer during back propagation, but now you're going from the last layer to the first layer to calculate the loss gradient with respect to the output activations. And then from here, the main thing is that you're computing the activation gradients. So determining how changes in activations influence the loss layer by layer. So now that you have the activation gradient in the final step, you use the activation gradient to compute the weight gradient. And this is how you're actually updating each of the weights during each training iteration. And so now you update your weights and you continuously do this until you have an error that you are happy with. And so that is kind of like, the concepts in NLP model training that the first section is talking about. So the next section that they're talking about is scaling training with stored weights. And so this is, talking about different types of parallelism that you can employ to, scaling training involves distributing computations across multiple compute units. And so there's two main types of scaling training. We have data parallelism and model parallelism. Oh, sorry, wait, let me read the comments. Okay, the comments are chill, or the chat, sorry, I just wanted to read the chat in case I was missing anything. So there's two main methods of scaling training. The first is data parallelism, and the second is model parallelism. And so, that is correct, Eugene. The weight updates are not done on the compute units, but the memory component, memory X, is what's actually storing the optimizer. So this is jumping ahead a little bit, but that is what's storing the optimizer. And so all of the weight gradients are streamed from the compute units to memory X. And then memory X is what's actually, has the optimizer computing the updated weights and then streaming the updated weights back. So you're not doing any of that on the compute units itself. But anyways, back to data parallelism and model parallelism. So there's data parallelism where you're splitting the batch of training samples over compute units, and then model parallelism, you're instead of splitting up the batch and the training data, you're splitting up the actual model. And there's two types of model parallelism that the paper talks about. We have pipeline model parallelism and tensor model parallelism. And so here's a diagram, figure 1, pulled straight from the paper that kind of illustrates this concept. And now going into data parallelism. So in data parallelism, you're storing a copy of the model on every single compute unit and sharding the training batch across the compute units. So each compute unit is calculating a partial weight gradient that's then summed up to give you that final weight gradient that's used to update all of the weights. The main issue with data parallelism is that every single compute unit must store the entire model. And this is a very large limitation for large models because this takes up a lot of memory. And so there's a variation of data parallelism called fully sharded data parallelism. Here, let me scroll to it in the paper right here. That kind of is meant to address this. And so in fully sharded data parallelism, model weights are distributed across compute units so that only one copy of each weight is persistently stored across the entire set of compute units. So if you look at the steps here, each compute unit is responsible for a portion of the model. And during the forward and backward computations, the compute unit that owns that, subset of weights broadcasts those weights to all of the other compute units. So, but then once those computations are done, each compute unit, erases all of the other weights and only like persistently stores the weights that it's responsible for. And so that is, so now the model just has to fit in the aggregate memory of the compute cluster. And then with model parallelism, there's two types of model parallelism: tensor model parallelism, pipeline model parallelism. Tensor model parallelism, you're splitting each layer across compute units. Pipeline model parallelism, you're distributing subsets of the model's layer across compute units. But the biggest thing to know is, there's a lot of communication overhead with model parallelism. You have to share activation tensors. And that is why in this paper, and in production, Cerebras focus on data parallelism. So all of this is mentioned in the paper as well. But model parallelism demands significant inter-server communication bandwidth, which, as you increase cluster size, just gets increasingly complicated. And now you have communication bottlenecks, and it just overall, you now have a very, very complicated system and implementation. So now that we have that background out of the way, we can kind of jump into weight streaming. And so weight streaming is where you separate model weight storage from compute. And so as I mentioned, what this means is that you're not storing your weights directly on the compute units, but instead on an external memory service called the memory X, which is an interconnect memory X, which is the external memory service. And so this is one thing that the paper mentions. So let me scroll to the paper to match where we are. So here, this is actually a new solution is needed, is kind of what this diagram is covering. So, you don't want to impose constraints on model size based on the memory available on the individual compute units. So, you want to be able to scale throughput, compute throughput with the computational requirements of the model. And you want to achieve scaling without complicated hybrid approaches to parallelism. So that's kind of this column right here. And then here we're kind of introducing this weight streaming solution. So instead of CPU, GPU processing, we're looking at the Cerebras CSX system, which, as I mentioned, is what's, the system that has that Wafer-Scale engine inside. And, we have significantly more on-chip memory, significantly more cores and transistors. So we're able to reduce the number of compute units to achieve an acceptable compute speed. Throughput, we're disaggregating compute from model storage, as I mentioned, that external memory service, memory X. And then we also have a new model for scheduling and coordinating the training work across the compute units. And so that's memory capacity, we have to hold, when we're training models, we have to have the weights, the gradients, the optimizer, and then interconnect, we're streaming the weights from the memory service to compute units. And then after those compute units, you do forward pass, backward pass, we're then transmitting the weight gradients back from the compute unit to the memory service. I think, as Eugene mentioned in the chat, it is the memory service that is actually, that stores the optimizer and is actually taking those weight gradients and updating the weights, and then streaming the updated weights back. So none of that is happening on the actual compute units itself. And so now to break down, as I've mentioned several times at this point, there are three main components of this weight streaming implementation. The first, as I mentioned, is that Wafer-Scale engine, the AI processor inside of the system The second is the memory X, which is the external memory service that stores model parameters, and then, as we've mentioned, the optimizer states. And then the last is swarm X. So this is the interconnect fabric that is transmitting, the weights and the weight gradients between memory X, the memory service, and our actual compute units. And this kind of abstraction and also having swarm X as the middleman actually allows, it black boxes a lot of things in terms of what the memory X sees and what each of the compute units sees. And we'll talk about it more, but it's really cool when we get to the swarm X section. And so, as I mentioned, this was a little bit covered in kind of my introduction in the very beginning, but going back, we have our AI processor, the Wafer-Scale engine, much larger than anything we've seen with the NVIDIA GPU, and it has 3 layers. And so on this wafer itself, we have the processing layer, which is all of our cores. We have our on-chip memory layer, which is, all of that SRAM that's giving each of our cores direct access to the weights and values, that it would need. And then we have that interconnect fabric. So we have, 2 fabrics. We have one fabric, which is the swarm X between memory X and the compute units. And then we have an on-chip interconnect fabric that is linking all of these cores together for very efficient communication. And so the Wafer-Scale Engine 3, as I mentioned, 900,000 cores, 44 gigabytes of SRAM, 4 trillion transistors. And I do add a note here that the paper focuses on Wafer-Scale Engine 2. And so the Wafer-Scale Engine 3 is, just an upgraded version of that. And so now looking at the memory X service. So this is the external memory service that is providing persistent storage for the model parameters and optimizer states. And just so in this entire system, you have one memory X, and it scales from 4 terabytes to 2.4 petabytes, supports models with up to 120 trillion parameters, and then it utilizes DRAM and flash storage. But memory X, it's very, very large memory. And so in this system, you have one memory X. You have that one like swarm X interconnect layer. And then you can have all of your CSX systems. So, you can scale the number of CSX systems up, and you just need that one memory X memory service. So you can kind of see that ratio here, one memory X, one swarm X, and then all of your compute units. And so the memory X has 2 primary functions. One, it streams the weights to the compute units. So it streams the weights twice. It streams the weights once during the forward pass to calculate the activations, and then it streams the weights to the compute units a second time to compute the activation gradients. Sorry, I'm catching up on the chat really quickly. Memory X also uses wafer chip to update values. Uses wafer chip to update values. I don't know exactly what you're trying to ask, but the memory X is using the weight gradients from the wafer chip to update the weight value. So the wafer chip is having to stream the weight gradients. The wafer chip inside of the CSX, which is our compute unit, does calculate, the activation gradient, weight gradient, streams that weight gradient back to memory X to update the weight values. So but then the memory X is what's actually updating the weight values. I think that's a clarification there. So going back to this, memory X, 2 primary functions. One is streams weights to the compute units twice, and then 2, it also calculates the updated weights. So it supports various optimizers, as I mentioned, like STD and Atom, and then uses that to calculate the updated weights. And one kind of side note, I don't know if it's really talked about too much in the paper, but optimizers actually require a lot more memory than the actual parameter. So optimizers require about 20 bytes per parameter compared to the parameter that's around like 2 bytes. And so even for a smaller model like Llama 8B, it will require more memory than what is just available on the on the chip itself, like that 44 gigabytes. And then, as I mentioned, this memory X can scale from 4 terabytes to 2.4 petabytes. So very, very lots of memory. And then the next component is the interconnect. The next and last component is the interconnect fabric called swarm X. And swarm X is what's connecting memory X to the different CSX systems. And it's what's, is passing along the weights and the weight gradients. And so during the forward pass, it's broadcasting the weights from memory X to compute units. During the backwards pass, it's receiving the partial gradients from each CSX system, reduces the gradients into a single tensor, and sends the aggregated gradient tensors back to memory X. And one thing that's really interesting, and I don't know if I did add a diagram, so I'll talk about this together. But nodes, right? And so quickly, the specifications: nodes with 100 gigabyte per second network interfaces, supports broadcast reduce operations 1 to 4, 1 to 2. What this means is that when you have each broadcast reduce will then communicate to either 2 or 4 systems. And so if you have 4 compute units, you have this one broadcast reduce going to 4 compute units. But if you have more than that, you can, see this kind of like this tree architecture where you have one broadcast reduce, communicates to 2 nodes, and then each of the broadcast reduce operations here are going to 4 nodes. So it's kind of a way to branch it. And also I realized that I need to scroll up in the paper or the paper is very behind on the left. Okay, here we go. And then finally, can memory X be used for inference, weight, broadcast functionality? So none of this is actually used for inference. So this memory X and swarm X, sorry, I'm answering the questions in the chat really quick. The memory X and swarm X, this whole weight streaming system is just used for training. So for inference, you're just using the SRAM, 44 gigabytes on the chip, and then you can network multiple chips together to support larger models. Yeah, Kyle is exactly right. Everything we're talking about right now is just weight streaming is just for training. Okay, so how do these 3 components work together?
Sarah,
Yes.
there's another question, which is what type of compute does memory X use? Is it like conventional CPU or something else? Would you know?
I am not sure. Let me see.
I guess the question is, what kind of compute does it use to update the weights? I guess this, the question people have.
Yeah, let me see let's see in the paper. I'm not sure, but I can look at it afterwards.
Okay, we can move on, and then we can just address this in the Discord channel. Thank you, Sarah.
But yeah, if you want to add that as a comment, I'll definitely address it or respond to your comment afterwards. If you just want to comment on the document, everyone has comment access. Okay, continuing on, or Daniel, if you want to jump in, if you know, Daniel is from Cerebras and is also here. But yeah, so these 3 components, as I mentioned, they're forward pass, memory access streaming weights to the systems, backward pass, the core stores the activation gradients in SRAM, which are used to compute the weight gradients. These weight gradients are sent back to memory X for weight updates. And then swarm X is just communicating between the weights and taking care of the communications between weights and gradients. And so one thing that's really, really cool that this cartoon kind of illustrates, this cartoon I think is actually not in the paper. I got it externally, but what this swarm X does is basically this memory X only has to send out one set of all of these weights. And then the swarm X then takes care of, distributing these weights to all of the compute units. So from this memory X perspective, it's almost as if it's only working with one compute unit. Like everything else is abstracted. And then from the compute unit perspective, it's sending all of its, like partial weight gradients, whatever it's calculated, back to SwarmX. And then SwarmX is aggregating everything so that it's only passing, one set of weight gradients back to the memory X. And so, like kind of with what you see here, it's like, okay, when there's one compute unit, one Wafer-Scale Engine 3, people are only seeing, like, all of this whole system from the user perspective, from the compute units, the memory units, everyone is almost like seeing one device, if that makes sense. Like the person is seeing one device, memory access seeing, it just like sends one copy. It doesn't have to worry about everything. And so there's a lot of like very beautiful abstractions that take place that really simplify, the understanding and like how all of this works. And then one other thing that I wanted to talk about. So this is a little out of order from what the paper has done it. And the paper talks about weight sparsity actually as part of the section on the Wafer-Scale engine, but I wanted to take it out or move it after just so that we can just like, talk through the three components of weight streaming and then, have this little distraction about weight sparsity. But the paper does talk a lot about weight sparsity as well. And so weight sparsity refers to the reduction of parameters by pruning insignificant parameters. And so a lot of the times in all of these matrix computations, there's a lot of zero and near zero values. And so in a dense representation, we're including all of these zero values. And in a sparse representation, we're removing all these zero and near zero values, especially when they result in like computations equal to zero. And so Cerebras leverages weight sparsity in two main ways during training. And so one is during that transmission by memory X through swarm X, and once is just like on the wafer itself. And so as memory X streams weights through swarm X, it eliminates zero and near zero values. And so this reduces bandwidth requirements significantly, pruning up to 90% of the data while maintaining accuracy. So the paper actually includes a lot of research on this as well. Looking at GPT-3, creating a sparse representation of GPT-3 and showing that, the performance is still and accuracy is still still the same. And then also mentions like the lottery ticket I think it's called the lottery ticket hypothesis, just also showing that model parameters can be pruned by 90% without a reduction in accuracy. And so basically Cerebras is able to really take advantage of this by one, eliminating these values between memory X and then the actual compute units. But then on the actual compute units on the wafer itself, each core in the Wafer-Scale engine also, it skips the computations for these zero and near zero values. So the core can recognize which values to skip, which values it did not receive, and knows to skip these. And so, it optimizes compute efficiency by only focusing on meaningful operations. And this next part is not, I don't think really talked about in the paper, but I'm sure people, to just add a little more context, it's like, why can't GPUs fully utilize weight sparsity? So there's two types of sparsity. One is fine-grained sparsity, fine-grained or unstructured sparsity, where there are randomly distributed zero values. And there's structured sparsity, where there are groups of zeros, for example, entire rows in a matrix. So both Cerebras and GPUs can handle structured sparsity, but GPUs are not designed to handle unstructured sparsity, whereas what I've just mentioned before is able to handle this unstructured sparsity. So that's like an additional thing that the paper talks a lot about. This very last section is the principles of operation. And so let me scroll down in the paper. And I believe this is the last section. And there's also a section kind of going over, what all of this looks like in, some of the actual work that's been done, but like, training models in the full COVID genome sequence, but that's not included in the notes. And so going back up here to the principles of operation. So this is the last section that we're really going to talk about. Oops, bad, delete that. Okay, so the Cerebras graph compiler, the CGC right here, integrates with machine learning frameworks such as TensorFlow and PyTorch. So this kind of, like, what is all of this, like, what does it actually look like? And so we have our compiler, and then what does it actually look like, the data on the chip, everything like that. And so this is what's compiling user models into binaries that can actually execute on this compute unit system. And then it natively supports the weight streaming that we've been talking about in this paper. And then how is this data actually distributed across the chip once it's streamed onto the chip? And so activation tensors and models like GPT-3 have 3 dimensions: batch, sequence, and hidden feature. And so the batch, that's the input samples, sequence is or the process, the tokenized input. And then the hidden feature is when we embed the tokenized input, the sequence, to form a 2D matrix S by H. And so this paper talks about, 2 different ways that you can take all these activation tensors and actually lay it out onto the Cerebras wafer. This is diagram 15 and 16 inside of the paper. And so we have S and H for sequence and hidden feature piling each layer, and then B is for batch. And so depending on the relative dimensions of S and H, you can, if S and H are very similar dimensions, you can lay it out on the wafer something like this on the right. If S and H have very different dimensions, you can lay it out something like this on the left, but both are valid configurations. And then the last little part is just talking about, the matrix multiplications used for all the phases, all the calculations is really just matrix multiplications. There's 2 types of matrix multiplication, one that supports one sparse input and one dense input. So this is when we're calculating the activation and activation gradient. And then one that supports 2 dense inputs and a sparse output, which is the weight gradients. So that's it for the paper. And then there's this optional appendix section that Sux recommend I add. I also use it. Okay, reading the chat. So I actually didn't dive too deep into these techniques. So I just kind of gave a couple of techniques and what different companies are doing, just so you're aware of it, and feel free to deep dive further. And so when we're looking at the different companies, we have NVIDIA Megatron, Microsoft DeepSpeed, and Facebook, or like Meta Farsec. And then we also, I don't know if they've previously presented on Paper Club, Swix mentioned Strong Compute's data streaming. But Strong Compute's data streaming is pretty different. It's more about, cluster management and, taking and like fully utilizing your cluster and like cluster orchestration versus, an actual, implementation where you're disaggregating model storage. Like basically no one is doing anything close where you're disaggregating model storage from compute. And none of these examples above do that either. And so, yeah, that's all I have prepared in these notes. I've tried to keep track with the chat, but yeah, feel free to add comments, add things in the chat. I think it's can memory XP used for inference. Yes, I see some hands raised. I think you can just drop it in the chat if you
Well,
haven't.
you can also just open out to Q&A. But first of all, rounds of applause for great presentation, and also drop the notion. I think we traditionally do Zoom applause, so it's just stream stuff in here. Okay, awesome. But yeah, Eugene, go ahead.
Yeah, I wanted to ask how much of this is